Okay.
Example, we have the example of a distributed load. So far we know most of we consider a distributed load because most of the examples we solve they involve point load. Now in the case that we have distributed load, the procedure is exactly the same. If I want to find the maximum stress, the formula is given sigma is equal to negative m over I times y. If your cross section is kind of symmetric, not arbitrary, on the y-axis, and this is your CG, or the geometric center, DT, geometric center, right? And this is your axis that you apply bending moment, M, and Y is computed from this point, this axis, Y, left to Y, positive Y, go up. And you can see that when you have bending moment like that, here is compression, this area is tension. You have this formula. And Y here is YXX, with respect to the axis that's in the center. So we have all these things. Now I want to apply to this problem where I have a distributed load. What should I do? Somehow, I either the first step is find moment of inertia or moment distribution. Okay? So the first thing that I do, I say, well, let's find the moment distribution. So in order to find the moment distribution, well, I do first external reactions here. So if you do external reactions, it's going to be 4K times 4 kilonewton, because it's symmetric divided by 2. Then you're going to have a 2K here, 2K here. Right? So then the next step is to cut it. How many intervals should I consider in order to draw the moment diagram? Just one. You see? There is no additional, like if I had a common moment here, you would consider from here to here and then from here to here. Just one. Right? So I just take a reference axis, for example, from left, and I cut it somewhere. Let's say x from left. And then this is going to be my system. So my FPD looks like to take the part of distributed load and bending moment here and axial load. This is 4 kilonewton per meter. But what is this distance from here to here? It's equal to x. From here to here is equal to x. So that's my FPD. Again, the key to draw the moment diagram when you have distributed load is to not replace it with a single load. If you replace that with a single load in the center, you wouldn't have anything here. And that's non-physical. Okay? So when you want to do that, first when you cut the beam, also draw the part of distributed load. Now, in this FED, the distributed load is kind of external load. But I include the internal load here in this part of system. Now, can I replace it with point load? Then I can replace it. After you cut it, then yes, you can replace it with point load. So here, in the step 2, then, the next thing I can do, I can replace this with a point load. What's the magnitude of this point load? The area under this, which is equal to 4K times X. 4K times X. And where is the location it's acting on? X over 2 from here, both sides. So from here to here is half of X. Alright? So 4K times X and then half of X. So I'm just ready to write equations. Right? Which one do I need? Because later we need shear and other things. Right now I need a moment. So I just immediately go to find the moment here. So summation of moments about this point, particular point X, 0. That will give you mx positive. These two don't have moment. And then you go to this one. This one is equal to 4K X. This is the value of force times the moment R. What's the moment R? X over 2. Positive or negative? Positive. Then you go to the next one. For this one, you have what? Negative 2K times X. Is equal to 0. Then I find my X positive, negative 2K X squared. So this is my moment distribution. It's kind of like parabolic, second order. Okay? Now I want to draw it. Why do I draw it? The question is why do I draw it? To find the maximum. But in the question, I don't say find the moment distribution everywhere. If I say find the stress distribution everywhere, what am I asking for? Field the stress. That's the question of field. That means the entire field, the stress. But right now, I'm not asking for field the stress. I'm asking for just a particular point that you have maximum stress. So you come here and say this is maximum when the top is maximum and the y is also maximum, right? So you should consider all different things to get the maximum. So if I draw that, how many points do I need? Let's draw it here. First, I evaluate it at x is equal to 0. What do I get? x0, moment is 0. What about x1? 2 times 1, negative 2, is equal to 0. Do not draw a line like that. But this is not a line. This is a parabolic here. What about half? Put x is equal to, so you get 2K times half negative 2K times 1 over 4. Then you get 2K times half negative 1K over 2. Then you get 1K over 2. For 500, here. Here. So you get, this is 500. And then I can now I have 3 points. Then I can connect this, but you don't connect it like that. You connect it like this, because this is a parabolic curve, second order. And you can check, to double check, you can use a calculator to plot it, some calculator plot function. And in the example test, I don't care if you have a calculator that can plot. Right? But that's not the point, everybody can plot it. So we can use that, or we can say, well, this curve, the coefficient of second order term is negative. That means the convexity is down. The direction of the parabola is down. So that makes sense with this. So this is my positive moment driver. Now you tell me where is the maximum moment? At the exact middle. Okay? And the value is equal to 500. According to that equation. Let's double check this 1K minus 1 over 2, 1K, 500. So now the next step is I come here and say, well, I got this guy, this is 500 and that particular point. And what is y and ixx? Now let's talk about this. Based on this position, let's say I find my centroid, and the centroid is obviously somewhere here, approximately. Right? If this was completely filled, the centroid would be exactly as center, but because we have more area at the bottom, this will shift down. Now I have two distances. Let's call this C1, C2. So which one should I use for my y, the maximum? C2. Alright? And therefore I know well this is C2. What about IXX? Well, I'll go back to the vector studies, last chapter, and I'll say I can cut this into two areas and then do the moment area calculation. So if I do that, let's break this down into two areas. Let's say this is 1. Let's say this is 1, and this one is 2, A2. Two areas. Now, I'll just say first the centroid calculation. I'll say, and also take your let's say take your Z from the bottom. Right? The reference, you can take it from the top. So I write Z bar for Z of centroid is equal to summation of Zi AI divided by summation of AI. And this I is from 1 to 2. Okay? So you get the centroid of shape 1, which is equal to, if that's 5 millimeter, what is that? 2.5 times, right here 2.5 times the area of shape 1, which is 5 times. From here to here is 10 plus 5 plus another 10 here. Right? So it's equal to 25 times 5. You see, the 5 times 25, the area times the distance from the bottom. You see, this is the reference for distance. So the centroid of that with respect to bottom is half of 5, which is 2.5. Then I'll go to the next one. Plus A2 times Z bar 2, or the centroid of the shape number 2 with respect to bottom. A2 is equal to 5 times 10. 5 times 10, like that. And the centroid is equal to 5. Half of this from here to here is 5, the center of that. Plus extra 5 is equal to 10. So that's times 10 divided by 25 times 5 plus 5 times 10. Put it in the calculator. It's 4 point. So this is equal to 4.64 millimeter. Don't forget the unit. So that's, let's check it. Is it right or wrong? Well, if you get, for example, if you get this from here to here is 15. Alright? So if you get, for example, 8, what is half of 15? 7.5. So from here to the half of it is 7.5. Now if you get 8, you immediately say, I'm doing something wrong. You go put it in the calculator again. But what did you get? 4, which is way below 7.5. Right? So it's kind of like, it's not validation. This is not called validation, it's called verification. That is it quickly, say, well, it's acceptable, it's not terribly wrong. Right? So we verified this. So let me draw a line to this point. So from here to here, I know that it's equal to 4.64 millimeter. Alright? So I just eliminate extra computation, open up some space. And now, the last thing I need to do, if I want to use this formula, is to compute IXX. So IXX is equal to, let's first do this one. This one, you go to the appendix, end of the book, you have a shape like AB, and with its local axis, I, let's say this XX, is equal to 112 A e to the third power. You have this formula. Now, use that formula, you apply it to shape 1. So you say total IXX for the shape is equal to IXX of this one, which is 112. This length, which is 25 times 5 third power, plus transfer to this from here, you see it's total axis to the centroid. You see parallel axis theorem. So when you use that relation, this relation is only valid about its local axis. When you transfer it to the centroid, you have to use parallel axis theorem. So the parallel axis theorem says the transfer moment is equal to the local moment plus time distance squared. So you say this one plus the area 5 times 25 times distance squared. Now what is that distance? The distance is from here to here. Right? So from here to here is equal to 4.64. Subtracted by from here to here, which is 2.5 squared. That's for shape 1. It's local moment of inertia plus transfer. Now you have everything for shape 1. Now you go to shape 2 plus the second line is shape 2. For shape 2, what do I do? Again, 112 5 times 10 cubed plus the area 5 times 10 times distance Now what is that distance? The center of that, which is 5 to here, plus extra 5, 10. So you say 10 minus 4 point from here to here. 4.6 square. These two together. So, if you do that, I would recommend you do that, I do it, and then we check our results. You know what I have to say here. We will do that. What is the dimension of that? We will do that later. What is the dimension of that? Millimeter to the force. Why? It's very important here to check the dimension. Why millimeter to the force power?
Because when you convert like powers to not in the first power, you have to like, let's say if you're converting millimeters to meters, you would have to like do 10 to the third 4 times.
Yeah. Yeah, but the question, that's right. The question that I'm asking is why we have the term like either meter to the force power or millimeter to the force. Why this is not second? Why this is not first? Why is fourth? Why? You see, the moment of inertia, if you go back to the definition, moment of inertia was integral x squared dA. Right? So what's the dimension of x? Let's say meter. So you have a meter square here, and area is what? Meter square. So meter square times meter square is to the power 4. So that's 4 that you see there, but sometimes we get confused. Say, well, area was second. Why did you get 4? Or vice versa. When you have 4, you put second. When you have second, you put 4. That's because of the definition of moment of inertia. So this number that I'm going to get, the entire summation is in millimeter to the force power. Why millimeter to the force power now? Because these dimensions that I use here, everything is millimeter. So I'm just consistent. Everything that I use is millimeter. So I expect the end result is millimeter squared. You could put a 10 to the negative 3 everywhere here, but that makes the expression to be very long. It's just intuitive. You can do that. So let's continue. So what I got was 2.60, 2.686, and 2, 3. 2.686 into 3 millimeter to the 4. Right? Did you get the same value? Yes. Alright. So now I have everything to substitute here and get my maximum stress. So I say sigma max is equal to maximum moment and max divided by xx, I'll call it xx, times C2, right? And what kind of moment is it? Positive or negative? You see, if I use this equation, there is a negative here. You know, I was in fact talking about absolute value. For the design, you mostly use absolute value. But if you want to report the sign, tension compression, you say, well, according to the equation, I have a negative sign here. So I have to also appreciate that. So negative Nmax divided by Ixx times C2. And I know that it's some sort of compression. Why? Well, you can conceptually show it. If you have this result like that, this is going to go like this, and everything on the top is going to be compressed. Everything in the bottom is going to extend, right? So it makes sense that the maximum at the top is compression, right? So I just plot values here. So I say it's equal to negative maximum moment, which was 500 times, you see, moment should be what? Newton meter. I have 1 over 2k, half of k. Half of k is just 500, that's the enough. If you have 2k, then you say 2 times 10 to 3. This stuff is easily to miss. Alright, so I have negative 500 divided by Ixx. I put 2.686 10 to 3. This is millimeter to the fourth power times. Then I say 1 meter is equal to 10 to 3,000 millimeter to the fourth. This is equal to 1, conversion factor. Vector studies chapter 1. 1 meter is equal to 1,000 millimeter. You divide together, you raise it to power 4, and then this is equal to cancel out with millimeter. So the end result is meter to the fourth power times C2. And what is my C2? C2 is the entire from here to here, which is 15 minus 4.6. I'm missing something right now. What am I missing? See? Look, everything is correct in dimension. This is going to be meter. This is going to be Newton meter. Everything is consistent. What about this distance C? C2 should be also meters. So if you have this, you have to multiply by 10 to negative 3. And this is then meter. So, now if you cancel out this will cancel out with here, right? And then you have meter square, meter to the fourth power here. So let's write the dimensions. So here, you have Newton meter on the top. You see, the bottom, you have meter to the fourth power coming from this resultant thing. And then right here, you have a meter times a meter. What do I get?
Newtons per meter squared.
So you get, this is meter squared with meter to the fourth power. The end result is Newton meter squared. What is that? Force divided by area. What is force divided by area?
Pascal.
Pascal, stress. You see? And it makes sense. On the left side, you have a stress. So when you do this kind of thing, in dimensional analysis, you have to get consistent results. All right, so let's put it in a calculator. So I get 1 point sigma max 1.9293 GPa. Too big. Negative. Did you get the same value? Just too big. So if you want to say, well, I I want to design, and this is my preliminary design, then you immediately say, go and revise. This is not going to hold. Why? But for a steel, you have like maximum sigma max is way smaller than this value, and it's compression. Some material behave different in tension and compression, like concrete. So in those stuff, the sign is extremely important. But is it compression or tension? You have a question? All right, next example. Cross section is the pipe. There's a new cross section. This diameter E2 is equal to 5, 15 millimeter. R2 radius 2, R1 5 millimeter. So yeah.
Is the line on the right side a wall also? What is it?
This is a rigid plate. So if I want to show it, this is a rigid plate that we actually welded at the end of this. Okay? And as a result, you can see that when I have this distributed load, this rigid plate is going to cause this both tension and bending. You see that? Because both tension and bending. Now, the question here is, find sigma max. So, if I want to do that, there are a lot of different ways that you can do it. You can take this thing at the system, draw a Philly. How many unknowns do I have if I take that system at a Philly? If I take this as a system, how many unknowns do I have? 3. 1, 2, 3. Everything here is known. And this is massless and rigid. So it's kind of, it's only here to apply this load uniformly to that. This is one way. The other way is you can say, I can replace, but I'm not going to cut this rigid. This is not what I'm interested in. I'm not going to find maximum sigma in the rigid plate. Right? So, in fact, this is not important. So I can consider it as an external load on that. So you can replace this with a point load here at the center. And then at this point, you can move it to this point. You can say I have one load, axial load on this beam, and also one couple moment. So you can completely get rid of that by having one axial load and one couple moment. This is the second method. Both methods should give exactly the same result. Now, I use method number 1. If I use method number 1, which is I take the entire thing as system. Then I write here, I have, let's say this point is A, AX, AY, and A. That's all I have. There is no body force, there is no other for this also given in my system. So that's the system it looks like. Let's try it for you. Your system look like this. And this is it. You can replace it with point load. And here you have AX, AY, and A. And the magnitude of that is 2K times 1 divided by 2, 1K. And its location is equal to, from here to here is equal to 1/3 of meter. That's your system. Alright? Now, for equation that I have, I write summation of forces in the x direction is 0. The reason I bring distributed load is because your homework that I posted, right, it has a distributed load, lots of distributed load. So it's just a practice to draw the moment diagram. So sigma x is 0, L is equal to AX, plus 1K is equal to 0. Summation of force Y is 0. AY is equal to 0. That's the only thing I have in Y. And then the same summation of moment about any point. For example, A is equal to 0. Then you get MA. Positive, these two are 0. Then negative 1K times 1/3 is equal to 0. Now, I have my system, FBD equations, then what was the next step? Solve. So when you solve it, you get AX is equal to negative 1K, AY 0, and MA is equal to 1000 divided by 3. That's what I have. Okay? So, let's put it here. MA is equal to 333 divided by 3. Yes, MA equal to AY 0, AX is equal to negative 1K, negative 1000. Now, I ask you the question, can I draw the moment diagram for the beam? Yes or no? Can I draw the distribution of moment from here to here? Can I do that, yes or no? Why not? That's what I was trying to ask you in order to resolve. But this is very confusing, in fact. Now the answer to that is yes, you can draw it. Why? Because I know that I have everything on the left one. Sometimes they're coupled. Sometimes you have something here, you don't have something here. But you have everything on the left one. So if I cut it at any point, say x from there, and I take only this as a system, then I'm going to have 3 unknowns here. But everything here is known. So still I can find it. So before you actually do it, do some sort of planning. And if you can do it or not. If you don't, then you have to do some other things. So, let's do that. Then you say, this is my system. I already have x component, -1000, right? So when you see AX was -1000, this way, the external reaction. So I can do this, that's completely right. Or I can make it this way and make it positive. Either way. But when you flip it, please change the sign. This is one of the things I'm great. I see everything is right, but the end result is not right. Then it's too long. I don't really have time to read it. So then I suspect, oh, maybe he just flipped the vector, but he didn't change the sign. And I go and say, oh yes, that's exactly the problem. Everything is right, but you didn't change the sign. So make sure you do that. AY 0, MA is equal to 3, 3, 3. I don't like this kind of numbers. They're kind of like cursed. 6, 6, 6. I don't like them. I like them. I'm not going to get the right result. But then I go here. What do I have here? MX, VX, and NX. Always think about those things. Usually we do only MX. But in this case, we actually do have axial load. We have chapter axial load. Don't forget that. Right? So you should consider NX in analysis too. Don't eliminate it. But if you don't have any axial load effect, don't waste your time with NX. Just put 0 there. But here you do have something, so you put NX, VX, and MX. So then I say for this system, now system changed. First I took the entire thing system, found the external reaction. Now this is my second system. For this system, summation of force in X0, -1000 plus NX is equal to 0. Summation of force to Y0. That will give you dx, the negative sign. What else do I have in Y? Nothing. Equal to 0. And then summation of moment about any point, which I take point X, right here, this point, X. Should be 0. That means positive mx, m of x, 0, 0. What about this? Moment comes from this. 0, and then plus 3, 3, 3 is equal to 0. Then you solve. Solve. Axial load is equal to 1000. Shear load is equal to 0. And moment at any x is equal to negative 3, 3, 3.3 Newton. And this is Newton. And this also. So, moment is negative. Everywhere in the beam, what does it mean? That the convexity is down. The curvature is down. You remember we defined positive when the curvature was up. Now the curvature is down. Does it make sense? But if I have float like that, then this is going to go down. Right? So it makes sense. Another thing, if I had something like this here, just the opposite of that, what would be the curvature, up or down? Zero. Nothing. Zero. Why? Because the moment becomes zero. This effect, if you do the same thing from scratch, you realize they make zero. They cancel each other. The only thing you get is the axial load, right? But here, I don't have that, so I get some moment because it's not symmetric. Okay? So I found my M. Found my M. So if I want to draw the moment diagram, let's draw the moment diagram and normal force. So this is my X, and this is my normal force at X, and again X, my moment diagram at X. Then for the normal force, I have a positive 1,000 everywhere. Positive 1,000 from here to here. Positive 1,000. That's normal force diagram. Shear is zero, and then I go to the moment. The moment is also negative. So you have something like negative 3.8. So these are given. Now I say the stress, the max stress. Now, if I say, now this is important. If I say, well, the max stress is equal to whatever sigma moment max that I have is 3.3. Divided by, I find the moment of inertia times y. And what is y? Y is?
Outer radius.
The outer radius. Why? Because the centroid, where is the neutral axis? The center line. It goes through the centroid. The centroid is right here. Y over there, if I want the sigma to be max, this y should be maximum distance from the center line, which is the outer radius. So I have everything, right? So can I just simply write sigma max is equal to m max divided by I xx, so I have this now, and times radius, the outer radius. Can I do that? Yes or no? No, let's say I have all the values ready to plug in. That's because you see what's going on here. You see, we had something in last class. We had principle of superposition. That means that you can take two phenomena each at a time, right? So yes, I know that this load right here, it caused some sort of bending, right? And I should use that, yes. But I have to consider another phenomenon, right? Not simultaneously. What is the other phenomenon? When you have axial load, what happens here? This is going to stretch. What does it mean? That means it brings additional stress at any point. So what do you need to do to add? Because these are two linear different phenomena. You need to do superposition for both of them, right? So you have to add them together. So let's do that. So if I do this, if I draw that, I know that everywhere I'm going to have 333.3 Newton meter everywhere. That means the sigma, according to that equation, is everywhere. But where is the maximum? On top. You see that? The maximum on top, which is tension, on the bottom is compression. On the other hand, I have a tension, pure tension, that is equal to 1000. And what is the sum of that? Always tension. So you have one thing that is always tension everywhere, and then you have a bending that is only tension on the top and compression on the bottom. So what point should I consider as a net summation of both of them? Top or bottom? Top. Top. Because the bottom, you have some sort of subtraction coming from the bending moment. Now let me draw it. So sigma max, I can write is equal to sigma max due to bending plus sigma max due to axial load. Right? For that, I can use this equation, negative m I x x times y plus n is equal to divided by cross-sectional area. Well, let's plug the value in. If you plug negative 10 here, you already have a negative. Negative 10, negative, positive. And this is also positive. So at y positive, that means up. The outer radius, you get the maximum function. You see that? Now the question is, let's solve the bigger problem. Let's solve for the stretch field. Not at the point, right? Let's solve for the stretch field. That means if you consider this beam, let's draw it in 3D, right? Let's draw it in 3D. Let's say you have any section, you cut it at any section here, right? Like that. And let's say this section is located X from the left and from the center Y. Now find sigma, the stress, that the normal stress is a function of xy. Like Cat 2 problem, function of several variables. So this is called a stress field because it gives you stress everywhere in the beam. So what should I write for that? I have, according to this equation, sigma x and y is equal to m, well, m of x, this is an easy thing. M of x is always constant. So negative times negative 3 is positive negative m of x divided by ixx. Does it depend on the location ixx? Everywhere I have the same cross section, right? So let's first compute ixx and then we plug it there. Ixx is equal to, then you go to the table, you see if you have a circle or a cat, ixx is equal to pi over 4 the radius to the fourth power. That's the equation you get from the appendix. So if I want to do ixx for something that you have empty hole here, then you say pi over 4 the outer radius 5 to the 4th. Which one is 15? 15 is the outer. Yeah, 15,000, sorry. 15 minus pi over 4 times 5 to the fourth. Don't forget, what is the unit? Millimeters to the fourth power. So you have to sum at some point multiply by 10 to 12. So put in a calculator. So that is equal to 39, 20, 27, 10 to 3. Let's go ahead and multiply by 10 to negative square root. And then I can put it here. So what should I put here? Back to this formula. I put 3, 9.27 times 10 to negative 9 for Ix. Right? Times Y. Should I plug maximum outer diameter for Y? If I want to find the stress field for X and Y? No. Right? I take, because this is arbitrary Y. Then I can evaluate it at Y max to get sigma max. So this, I'm trying to find sigma versus X and Y. Right? So that's going to be multiplied by Y plus N, which is 1,000, divided by cross-sectional area. Now, another mistake they usually make is they say, well, pi, the outer diameter square. But look, what is the cross-sectional area that I have? The net area is equal to the outer minus the inner. So here you have to put pi times the outer is 15 square minus 5 square. So it's divided by 6, 28.3, 10 to negative. This is in millimeter square. Then you multiply by 1 meter, 10 to 3 millimeter square. They cancel out. 10 to negative 6. That's it. So you see your stress field, it's a function of Y, but not a function of X. I may give an example in the test that a stress field is a function of X too. How can it be a function of X? When your moment is a function of X. You see the moment is constant here. Now if you had a cross load like that, or a bending moment here, then the moment will depend on the X. Right? So now the question, optimization, find the maximum of that. Where is the maximum for that? Find the Y location of the maximum.
Positive Y.
Positive. Y is positive, because it could be, you see, this is positive, Y is not from here. This is positive 15, and from here to here is negative 15. So which one should I put there to get the maximum? Positive 15. That means everywhere on the top, right here. And it kind of makes sense because the moment you actually apply this bending moment here on the rigid plate, this is going to go nose down. So that means this bar is going to go down. Hopefully I can make a little graphic here. So it's going to go like this. And there you go. And then you see everywhere across, along this top line, everywhere here you have stretching. And here you have compression. And then you may get confused and say, well, if I have a stretching and compression, shouldn't be equal like the way we did before where we had PU moment? Because you have axial load. And because of principle of superposition, this comes from exactly superposition. So I consider only the bending effect, and then I consider only the axial effect. And then I sum them together. Right? Another thing, another problem. The last one. This is a meter weather. It's ready. And we have a very finite time. Let's make it a funnel. Let's make it a funnel. Let's say here the radius is R1, the radius here R2, and then you have a distributed load. This is 2K, 1K, and the cross section is just a circle, solid everywhere. What is a taper beam? So you have a different radius here, different radius here. It's a solid taper beam. And then you have a distributed flow from 2K to 1K. Okay? Now, let's fix to the wall. Let's say this is the wall. This taper beam is welded to the wall. So this is weld. See, welded to the wall, this is the load. Find sigma of x and y, the stress field. Final Weber. So the way we do that, you only have 2 minutes to think about it. Okay? And then you have to come here, and only one person can get it. Only one student. So if you can do it, just you can start doing it right now. It's the final layer, right? Okay, only one student. But keep going. I mean, if I say, well, don't do that, the entire purpose of these things is for you to practice. Distance here is also one. From here to here. from here to here is 1. 1 here. Let me draw a 3D version of how that is possible. Okay. Okay. And just put this in there. This could be the snow. It's just the snow. Too much of snow here and a little bit here. See it? But it's snowing. Then you have a kind of different load. You have too much here near the wall, and then smaller on the tip. You're going to the right way. Now you can when you go home, you remember in calculus 2 we had like the maximum minimum function of several variables, 2 variables, 3 variables. What do you do to find the external, the maximum minimum, the external? You take the gradient and make it to 0. Or derivative in one, when you have only one variable, take the derivative, make it 0. When you have 2 variables, take the gradient. So partial x, partial y, and make it 0. And then solve for the location. So go home, if you do that correctly, you're going to get a function of x and y. And what is x? The distance from the base. This is x. And what is y? Distance from the center, y. So you're going to get a function of x, y. Take the derivative, make it equal to 0. Then what do you expect to get for maximum stress? What point is the maximum stress? Huh? Just based on intuition, what point is the maximum stress there? To wall. Yeah. And what point on the wall? We have, you see on the wall, we have a lot of points here. What point on the wall? The top. The top on the wall. See that? So you have x0, y is equal to R1. interestingly, when you go home and do that derivative and solve mathematical equation, when you solve it, you find x0 or 1. It's perfectly matching the physics intuition. But that's for like a machine interpretation. Somebody who doesn't have any intuition. Your computer can't solve the problem. By just taking derivative, making it equal to 0. Well, let me solve this next class, because this is a good example. But what you can do in order to completely prepare for the next class, because next class we are going to cover the shear and also torsion together after I solve that.
Is the inertia right?
Yeah, the inertia was right. The original one was right. But the rest